Alright, in 6.1b, we're going to look at discrete variables and continuous. So we're going to look at the differences and how you handle those in this section. Okay, so we ended the last video discussing how to find the expected value of a discrete random variable. So we're going to pick up this one with discrete random variables again, but we're going to talk about how do you measure spread for a discrete random variable. Well, first you measure the variance of the variabilities. So there's a formula you'll have to know. It is on your chart, and it looks like this. Now variance is sigma squared. It's the standard deviation squared. And the way you find variance is you take each outcome, so like this outcome, subtract the mean, square it, and then multiply it by that outcome's probability. And you do that for each possible outcome in the distribution. And then you add those products up. That is what we call variance. And we do have to use this a couple times in probability, so it's important you know this. But most importantly, you have to find variance before you can find standard deviation, because standard deviation is the square root of the variance. Alright? So you have to know how to find variance first. So, okay, let's say we've done that. How do you interpret a standard deviation? Well, it's always the average distance, whatever the outcomes are, from the mean. So obviously you would want to put that in context of the question, but the phrase you want to keep using is the average distance from the mean of whatever scenario it is. So we're going to go back and look at that languages example we used in the last video about how many languages an average high school student speaks. Okay, and we're going to use our calculators in a moment to find the standard deviation. But first I want to walk you through what does it look like to calculate variance. And what do you need to show for work? Well, variance looks like this, right? It's the outcome minus the mean that we found in the previous video, squared, times its probability. And then I go to the next outcome, 2 times the mean squared times its probability. And then I could just put dot, 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 and then be done with it, okay? I've shown enough work here that I know the idea. When I've done this, and in my calculator, I get this value. But remember, that's variance. That's not standard deviation. So to find the standard deviation, I take the square root of that value, and I get 0.671. Now I have to interpret this. Well, I would say the number of languages a randomly selected student speaks will typically vary from the mean. There's the phrase, which was the mean of 1.457, about 1.671. Okay? So typically vary from the mean. That's the key phrase anytime you are interpreting a standard deviation. Now, how do you do that in a calculator? Well, it's pretty crafty. Here we go. In your calculator, you're going to put the outcomes in list 1, and then you put your probabilities corresponding to them in list 2. All right? So once you've done that, you're going to go back out to stat. Here's what it looks like in list 1 and list 2. And I'm going to go stat, calc, and then I'm going to go one variable statistics. And the list I'll need to make sure it says L1. And you'll need to put frequency list as L2 because you need it to reference the probabilities. Once you've done that, and get them to the right list, hit calculate, you're going to get this outcome. There's a lot on here, but really there's 2 things you need to focus on. Here's the mean, the expected value we calculated by hand previously. And down here is the standard deviation we just did by hand. But you can definitely use your calculator to find those. You just need to show some work like this on your paper, so you're not completely dependent on the calculator. Okay, so now that we've talked about how do you find mean and standard deviation of a discrete random variable, we're going to switch gears and go to continuous. So let's just refresh for a moment. What is a continuous random variable? Well, it's a variable with no gaps in between the values, okay? Usually I think of this in terms of a measurement because there can be decimals to every measurement, okay? For instance, a continuous random variable is foot length. If I measure your foot, it may not be exactly 12 inches. It may be 12.12 inches or 12.0002 inches. It's never going to be exact. So there's decimal values, or the time it takes to run the hurdle, 110-meter hurdles, or your actual age. Okay, you know this when you talk to a kiddo who's 5 3/4 years old. Okay, they don't just say I'm 5, I'm 5 3/4. So there is a running decimal to your age, actually. Now, discrete, remember we talked about discrete. Discrete variable with a foot is your shoe size. We package it in little units of shoe size. The discrete version of the hurdles is actually the number of hurdles. You either crossed one or not. And then lastly, the number of birthdays that have passed is a discrete number, okay? So continuous, think of it as measurements, things that can have decimal values, all right? Is it possible to have a shoe size of 8? Sure. Is it possible to have a foot length of exactly 8 inches? Probably not. It's probably more like 8.124 inches, for instance, okay? So that's one way to think of the difference between a discrete and a continuous random variable. Now, how many foot lengths are there? Well, if you think of foot length in terms of decimals, there's infinitely many possible lengths out there. So then how do you graph the distribution of it? Well, if we made a histogram of all the potential outcomes, it would be hundreds of tiny little rectangles. Okay? Each little bar would be so small because there'd be so many values on our x-axis. It would be so crowded, it basically turns into your density curve that we've talked about before in Chapter 2. So then how do we use that to find probabilities for continuous random variables? We find, indeed, the area under the density curve. Okay? So then think about this. Is the probability of x is less than a, how is it related to the probability of x is less than or equal to a? When we did the example before with discrete, we had to make sure we included the a value on this one and excluded it on this. So how does that work with continuous when you have decimals like crazy? Well, here's the deal. The areas will be the same, actually, because the boundary line that contains the a value really has no area. It's so teeny tiny, that rectangle is so tiny, it has no area under the curve. So the probabilities you get for these two types of inequalities will look the same with a continuous random variable. All right, so let's walk through an example of a continuous random variable. So the weights of a 3-year-old females closely follow a normal distribution with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Randomly choose one 3-year-old female and call her weight X. All right? Part A says find the probability that the randomly selected 3-year-old weighs at least 30 pounds. So there's a 3-step process to answering this, okay? First step is you draw the normal distribution that's mentioned. Draw it, and I label it. Now, this is very important, this notation right here. N is for normal, and we always put mean and then standard deviation. Then we draw the curve, and if you recall, the mean falls right down the center, so I label that. And I have my standard deviation here and I'll need it in a moment. Now, I look at the question, it says at least 30 pounds. Well, if 30.7 is right here, 30 is slightly less than that. So I'm going to draw a boundary here, and I'm going to shade greater than because it says at least. That means it can be more than. So this is the area under the curve I'm looking for. Now, in probability speak, remember at least would mean including 30. But we just said that in continuous random variables, that's the same thing as greater than 30. So in step 2, you're telling me what's the probability saying. And you're going to use, in your calculator, a table that's called norm CDF, and you hit second bars and number 2, and it's going to pull up this menu. It says normal CDF. It's cumulative distribution function. And notice that it has some prompts here that you have to fill out. So you have to tell it what's the lower boundary of your shaded region. So in this problem, our lower boundary is 30. Our upper boundary, just use a really large value, like 10,000. Doesn't really matter, just pick a big value. The mean, use the mean in the context of the question, 30.7, and the standard deviation is 3.6. Okay, on your paper, what you're showing me is the drawing over here, your probability statement, and the norm CDF stuff, so I know what it is you put in your calculator to get whatever answer you do. Okay, LB is for lower boundary, upper boundary. So in my calculator, this is the answer I got. It was 0.5771. And then the third step to my answer is an interpretation. there's about a 58% probability of randomly selecting a 3-year-old female who weighs at least 30 pounds. All right? Okay, in part B, same question. Find the probability that a randomly selected 3-year-old female weighs between 25 and 35 pounds. So the first step is to draw the normal curve, label the center, and label the values in question. Here's 25 over here, 35 over here, and I want the values, I want the area between those. Notice I put my normal label on it with the mean and standard deviation, and I've shaded. Now, do you have to do this for every question, every part of every question? Yes, because you're shading different portions of the normal curve for each part. Now that I have my curve, I can then think about what's the probability I'm looking for. So I can put my statement in. Probability that x is between 25 and 35, right? So in my calculator, I'm going to that same menu as before. My lower boundary this time is 25. My upper boundary is 35. The mean is still 30.7. The standard deviation is still 3.6. And it gives me a value of 8.8272. So then I have to do my third step and interpret. It says there's about an 83% probability of randomly selecting a 3-year-old female who weighs between 25 and 35 pounds. Okay? Part C, different type of question. It says if the probability of x is less than k, if that probability is 80%, what's that value of k? So you have to think a little backwards here. So first draw your curve, like we've said before, and label the normal values. Now, 80% under the curve. So if you know the mean, right here is 50%. 80% is a little more. So I'm going to shade over here. And I'm going to draw a boundary and label it K. I need to know what is that value right there. Okay, if 30 is here, what does this need to be? Logically, it needs to be greater than 30. Well, how do I do this in my calculator? Well, you're going to use inverse norm, which is right under norm CDF in that same menu. And notice it asks you first, what's the area? Well, the area I'm looking for is 0.8. The mean is 30.7. The standard deviation is 3.6. Now, my calculator has an option that says tail in left, center, or right. Some of your calculators won't have that, and so that's fine. It's okay. It defaults to left, which is what we want. Okay. It's always looking at the area to the left of your boundary. That's what the calculator knows to do naturally. There are occasions you may want this, but we'll deal with those later. All right? So I've told it what area I want, and help me find that boundary point. That's what inverse norm does. So here's your keystrokes to get to inverse norm. It's just second bars and number 3, by the way. Here's the work I need to show for step 2. And you notice that the outcome it gives me is 33.73. And that makes a little bit of sense. It should be greater than 30, right? So that's a weight. That's a weight of 3-year-olds. So to interpret this, I would say a 3-year-old female has about an 80% chance of weighing 33.73 pounds. All right, so that should give you some idea of how to work continuous random variable problems.